J4Z half the time. Well, welcome to our clubhouse this evening. I'm going to be doing a presentation on vertical antenna arrays. So a lot of you guys are familiar with running a single vertical or a dipole or a loop antenna. Louder? Yes. Do I need to start again? Okay. Sorry about that, folks. Thought we had some audio problems. But anyways, so you're familiar with running a loop antenna or maybe a dipole. And a lot of us don't either have the space, the funds, or the allowances by our spouses to put up towers and big antennas. But if you have proper space, a vertical array may be a good solution for you. A single vertical will get you a pretty good output, low DX radiation angle. So let me start the presentation with vertical arrays. They're very easy to build. You can deploy them rapidly. It's possible to rapidly switch directions. You have good low angle radiation. You have good front to back rejection characteristics. They're very efficient, and for the most part, they're fairly broad banded within a band. And the disadvantages, depending on the band, they may have a large footprint, and they require quite a bit of wire to put together. Some of the stuff we're going to talk about, some terminology. If you're fairly new to ham radio, these may not be familiar to you, so I'm going to go through them. If you're a seasoned veteran, like some of us, it's probably a little bit of remedial education, but bear with me. So you have a radiator, which is the radiating element of the antenna, sometimes called a driven element. You have radials, which are basically the field underneath the antenna. They're the negative side of the antenna, let's put it, or ground. Isotropic antenna. Now, this is a theoretical antenna. It's basically a point in space that is a perfect radiator, so it's unity gain in all directions. It's basically a spherical unity gain, so whatever you put in an antenna comes out of that antenna. Decibel, we should all be familiar with that. It's the power unit for RF power. Parasitic array, okay, that's an array with multiple elements, but only one driven element. You don't have multiple driven, you have one driven, and the rest of the elements act as a parasitic or mutually coupled to that. Antenna to gain is efficiency plus directivity, and is measured in dBs. Angle of radiation, that's your takeoff angle. So the lower the takeoff angle, as you know, the better your angle is going to be off the atmosphere when you bend the beam off of the ionosphere, so you'll go longer with a lower radiation angle. Front to back rejection, that is the difference of what you can hear on the front side of the antenna versus the back side of the antenna. And that helps with when you're in a pile-up or you're working contests. You want to have a certain area of the world you're looking for. It'll keep all the noise from the areas you don't want, or all the signals from the areas you don't want coming in to your antenna. And then directivity is basically the ratio of the transmitted power and between the front and the rear of the antenna. Okay, so vertical antenna design. Most of the time when you're dealing with a vertical antenna in the HF band, you're going to do a quarter wave, okay, and it's going to have radials. You'll see some that have counterpoise, which are basically raised radials. You'll see some that have no radials, but they run counterpoise. The imperial formula for feet is 234 divided by the frequency in megahertz times the velocity factor of the wire. Okay, as bare wire has a higher velocity factor than insulated wire, so the RF travels slower down that insulated wire, so you have to compensate for that. And for typical like THHN or a typical antenna wire that you might pick up from DX Engineering or Wireman, that's going to be about 93% of the speed of light. So you would multiply whatever that length is times 0.93, and that would give you your length. Okay, and the metric formula is 71.1. Now, I typically use 300 divided by the frequency in megahertz, and then divide that by 4. I think it's a little more accurate measurement, and then multiply by my velocity factor. But the formula that most books you'll see say 71.1. Radials can be any length. Okay, so if you have a small garden or a small backyard where you don't have a lot of room to lay radials out for a tall vertical, you can cut those radials shorter. You just have to make up about 2 wavelengths is ideal. Once you get past 2 wavelengths of radials, you're really looking at diminishing returns. Okay, the more radials you have down, the better that antenna is going to radiate. But when you get past 2 wavelengths, sometimes 3 wavelengths, the return on the investment of the time, the material, and the frustration of laying radials, if you've ever done it, doesn't warrant the minute gain you're going to get in your output of your antenna. And then some quick tools. There's a bunch of websites out there that will help you get your antenna lengths. If you don't want to do the math yourself, you can plug in what frequency you want, and it'll give you your length of your radiator and the length of your radials. So those are cool little websites. Okay, so what I did is I modeled this in MMANA, which is a modeling program. It's a single vertical antenna, cut for 40 meters. And if you can see, you have the antenna and you can see the current pattern. It's a vertical pattern. The screen on the left, on the lower left, is the top view of that radiation pattern. It's basically a circle, okay? It's actually a donut, okay? So you have a lobe on either side, as you see on the right, and that continues all the way around that antenna, okay? So that's a typical radiation pattern for a single antenna, vertical. It's going to be a big donut of RF around that, okay? Now, you do get some gain with that at certain angles because in a perfect world, it would be a sphere, but because you have radials, it forces the radiation out in a donut shape versus a sphere, okay? So, if we want to get gain, okay, now getting a gain off dipole is possible. It's not going to be high gain. Getting gain off of loops, possible. The bigger the loop, the more gain you get at higher frequencies. But it's very easy to get gain with verticals, okay? You take it and you do it one of 2 ways. You either add elements or you change the position of the elements, okay? So with a simple design of a 2-element parasitic array, okay? So now you're taking 2 wires and suspending them vertically. Most people will put them on a fiberglass mast. And what you do is you have one antenna, you feed it with coax. The other antenna is going to be your reflector. You make it slightly longer, usually about 10%. So let's say we were looking at something at 72, 7.2 for 40 meters. You would want your reflector to be at about 7.35, okay? So it's got, 6.95. You want it to be a little bit longer, okay? And then you would short the radial field and the radiating element on that antenna. So now you've built a reflector. So it's similar to what a Yagi looks like when you're talking about a horizontal antenna that's up on a tower, okay? And you get a pretty nice cardioid pattern out of that. If you look on the bottom left, you can see how that donut gets compressed because you have a radiator, or a reflector behind the radiator, and it's pushing that RF forward, okay? And then you can see on the side view, or the street view, you can see where that lobe, that stronger lobe off the front, has more gain, and it's less pronounced in angle than the front lobe, okay? So you're pushing all that RF, you're squeezing it down. Now that's a parasitic array, and it works really well. It's over a single element. A single element antenna, we were talking about a single vertical. Max gain is 1.29 dB at 26.5 degrees, give or take. At 10 degrees, where you start to get into really long distance DX, that 5 to 10 degree takeoff angles where you're really long DX. So from here, we're talking other side of the globe. We're talking India, you're talking South Pacific, Australia, those areas. In the mainland China, you're looking at somewhere between 12 and 5 degrees of radiation angle. So I measured it at 10 degrees, and it's negative 1.4 dB. So that means whatever I'm putting in that, I'm putting in, 100 watts into that radio, and I've got perfect coax, no loss in the coax, and I got 100 watts going in antenna. At 10 degrees, I'm 1.4 dB down from my input. Okay, so I'm losing it because I'm squeezing that up, and I'm getting 1.29 dB at 27 degrees. Okay. The 2-element parasitic, the max gain on it is 5.26 dB of gain at 23 degrees. So almost the same takeoff angle for the main lobe, and you're 4 dB better. Okay? So you know when you talk about dBs, 3 dB is double your power out. Okay? So if I put 100 watts in to that radio, into that antenna from the radio, and I have perfect coax, so let's eliminate the coax loss. At 23 degrees, 24 degrees, I'm getting almost 200, almost 400 out at that angle, okay? But I'm sacrificing on the back side, okay? So I'm taking all that RF and squeezing it. When you go down to 10 degrees, I'm 2.9 dBi plus. So now I'm 3 dB better than I was on that single vertical radiator at that lower. So I've doubled my output power at that angle, okay? So my signal's going to be a heck of a lot stronger when it gets to where it's going than it would be if I use a single vertical, okay? The bad thing about using a parasitic array, for the most part, it's directional. You can't really change the direction very easily, okay? Now you can put a coil of wire and move that coil back and forth to make one longer than the other, okay, on the 2 elements, and you just swap your coax around. Or you can do it electronically. You can build a little box sitting out there with a coil in it and switch it in and out, okay? Now when you start talking about a phased array, which is much easier to switch, it's a little more complex to build, but allows more efficient transmission, okay? You have a lot less loss in a phased array, and it's easier to change direction. You use a specific length of 75 ohm coax to delay the signal to the second antenna, okay? So we're going to still have those 2 verticals up, but I'm going to make them the same length, okay? And now I'm going to switch in a piece of coax that's 75 ohms at 71 degrees on a quarter wave, and I'm going to use that to delay the signal to that second radiator, okay? So effectively, I've made it a reflector in a way, right? It's not truly a reflector because I'm feeding 2 at the same time, and I'm phasing that signal. So I got one signal going out a little earlier than the other, and they create an interference pattern. It's constructive interference, okay? So if you understand how waves work, when you're 180 degrees out of phase, they cancel. But when you're just a little bit out of phase, you can add at certain points, okay? So we end up using a 71-degree piece of coax at 75 ohms for a quarter wave. And there's a formula for doing that. If you look at the online calculator, YCARS-antenna.co.uk/coax-phasing.calculator, it gives you a really nice little calculator where you put in the frequency you want, and it'll tell you how long to cut that piece of coax. And you can use RG6 or you can use RG11. If you're running power, I would run RG11. It's a bigger coax. It's a lot less lossy than RG6. And you can build these things yourself. Again, it's going to take a little time, and you have to have patience. What you do is you cut that coax to length, what the calculator tells you to cut it, and then you put an end on one end, you leave the other end blunt. And you adjust your SWR meter. You look at just the true impedance, the resistivity of the wire, not the reactivity, just the resistance of the wire. And you cut it back. When it goes to 0, you have it exactly right for that frequency, okay? Now, you're cutting for a specific frequency, but that doesn't mean the antenna is just going to work on that frequency. It's going to work on, it's broadbanded. It'll work, if you cut it for like 7200, you're going to have less than 2 SWR across the whole band. It's just, it's keyed in. You're going to have the lowest SWR at 7200, okay? And then you put your other piece of coax on, and other connector on your piece of coax, and you're good to go. Now, There's a gentleman, and I forget his call sign, his last name's Chrisman. They call it the Chrisman Method. And what he said to do is to use two 84-degree pieces of 75 ohm coax at a quarter wave to feed both antennas, and then you switch in the 71-degree piece. What that buys you, because you're taking the power and dividing it between two sources, you drop your resistance, okay? So your resistance goes from 50 ohms to 25 ohms because you're dividing it, okay? If you use 75 ohm coax, you're at 35 ohms, which is pretty much the native resistivity of, or impedance of a single vertical. It's right around 35 ohms, okay? Now, does it matter that much? No. If you don't want to cut two 84-degree, 75 ohm phasing cables, you can use two 50 ohm pieces of cable. It's just not going to be as efficient, and your SWR is going to be a little bit higher, okay? Not by much, right? You're still going to be that under that 2.0 for the whole band. It's just going to be 1.8, 1.9 versus 1.5, 1.4, okay? In the grand scheme of things, is it worth it? I don't know. You might get a little more efficiency out of the antenna, sure, why not, you know? But it's very simple circuit to build. You build a relay, okay? And on the normally open and the normally closed part of a relay, you put your two feeders out to your antennas. And between the normally open and normally closed, you put in your phasing line. So whatever way you switch your relay, whether it's on the normally open position or normally closed position, you're feeding one antenna straight and one antenna with the 71 degree phase line in it, okay? You see how that works in that diagram? Okay? So that's the easy way to do it. It's the Chrisman method. It works very well. It's very easy to build. It's a simple circuit. It doesn't cost a lot of money. You can buy a nice relay for about 15 bucks, and you can run power through it. 600 volt, 30 amp relay, you know, single pole, yeah, 15 bucks. You put a couple coax connectors in there, and you're good to go, okay? So let's look at a two-element vertical phased array, okay? Now you see on the diagram of the antennas there, where we have the two verticals, there's feed points at both those antennas, okay? So now we're feeding both instead of just one. And that cardioid pattern is really nice and tight, okay? It tightened it up. You see a distinct null back there, so it means you're forcing more RF out the front of that antenna. And even your side pattern, the lobe is a little cleaner and a little lower in your takeoff angle, okay? You have more gain at a lower takeoff angle. We compare a two-element phased array to a two-element parasitic array. The parasitic array is 5.26 dB a gain. The phased is 5.53, okay? Now, it's not that much difference in gain. It's 0.3 dB. Is it really worth it to build that phasing box? Yeah, when you consider I can flip a switch and turn that thing from east to west or north to south, and I have two directions now. When I was covering with a parasitic array and not able to switch it easily, I had 120 degrees of coverage in the beam width. And when you talk about beam width, you're talking about maximum gain and 3 dB down to either side. Okay, so if we were talking about the parasitic array at 5.26 dB a gain, max gain at this point, when I get to 3 dB this way down, so 2.26 and 2.26 this way, when you measure that angle, that gives you your beam width. With the phased array, or the vertical array, the parasitic that I had, it was 60 degrees either side, so I got 120 degrees of beam width on that antenna where it's really usable. Okay. When I use a phased array and I switch that, now I got 120 degrees in this direction and I got 120 degrees in this direction, right? So yeah, it's much worth it to have that phasing cable in there to be able to allow you to switch that antenna back and forth. And even with a beam, a high gain Yagi up on a tower, the time to rotate that thing, maybe a minute to go 180 degrees. This is instantaneous. You flip the switch on your desk, and that antenna goes from east to west, or west to east, or north to south, south to west, whatever direction you got it in. The other direction is going to be there almost instantaneously. So if you do spot a DX, pops up and it's on the long path and you're running the short path, and flip the switch and you're 180 degrees and you got your sights turned on them. So yeah, I mean, we get 0.3 dB a gain by using the phasing, but having that ability to swap that antenna around is definitely worth it, okay? Now, what happens when we do a 3-element parasitic array? So now we're getting into higher gain antennas. You have a driven element in the center, you got a reflector, and now you got a director. It's similar to a 3-element Yagi, right? These are good antennas. They will get you a lot of gain in one direction, okay? Again, you get a nice cardioid pattern. You're getting about 6 dB, 6.78, almost 7 dB a gain in a relatively short distance, right? The problem with these things is you can't switch them, right? Because now you've got to deal with 2 elements. You got to switch those lengths on those elements, because now you got one reflector that's really long at 6.95 megahertz, and you got another one at 7.35 megahertz, and you got to change those 2 wires. So you got to pick the pole up and take it over and walk the other one down and reset it up. Now, there is a way to phase those things, right, and put a switching network in, but it's a lot more complex than a 2-element, because now not only are you compensating the 71 degrees of phase angle, but you're also compensating for the lengths of the conductors or the radiators, so the elements of the antenna. So now you have to put in coils that make one longer, and you have to put in a circuit, an LC circuit, to make the other one look shorter. So it's a lot more complex. And for me, as a home brewer, I don't think I can build it as cheap as I can buy the phasing box from somebody. I can still build that antenna system, right, and design it, but I would go to DX Engineering and buy the box to change it out. Right? It just doesn't make sense to try and build that circuit yourself unless you're just really adept at doing it. I think it'd be more time and pain. But you also narrow that beam width down. All right, so now we're going from 120 degrees of beam width, right, on the 2-element, and you're taking it down to 84 degrees in one direction on a 3-element. So every time you push that RF harder and get more gain in one direction, you're squeezing down that bandwidth or that beam width as well, okay? So the effective gain of putting that 3rd element in, regardless of the switching, right, you're going to get another dB, 1.8 dB, so another 2 dB of gain, right? But you lose the switching ability. To me, it's not worth it. That's not enough of a gain for me to give up the switching. I would stay with a 2-element phased array versus a 3-element parasitic, okay? Now, what we built for field day this year is a 3-element triangular array, okay? And it's a little different animal. It's an old design. This thing's been around for probably since the 40s, okay? And for a while there in the 70s, it was a very, very popular CB antenna because it didn't have a big footprint, and it was real easy to build. But what you do is you feed 2 of these elements in phase. So you're going to feed all 3 elements, but 2 of them are in phase, and one has the 71-degree phasing cable in it to delay it. So it acts like a reflector. So now I have 2 elements driving and 1 reflecting, okay? And in principle, you could take one of them and drive it and put 2 reflectors behind it. It really doesn't make sense when you look at the pattern of how this thing covers when you talk about a switching network on this. It'll give you true 360-degree coverage and instantaneously, but you're giving up some things, okay? And it's a lot more of a complex circuit to build, okay? But let's take a look at it. So you can see up in the upper left-hand corner, we've got the 3 elements. The front 2 with the shorter gap between the red and the black, which is the currents on it, are the 2 driven elements. The one in the back is the reflective, or the reflecting element, or the delayed element is the proper term. And you can see the cardioid pointer. I put a 3D representation on there so you can see it in 3D. It's a little easier to visualize. than the top view and the map view, right? So you get a really nice cardioid pattern, very high gain, one direction. We'll look at the specifics. So the parasitic was 6.78 dB of gain, okay? The 3-element you give up about a dB of gain, right, by having a 3-element triangular array. The front to back is a little better on the 3-element triangular array than it is on the 3-element straight parasitic. The beam width is wider on the 3-element triangular. You're 96 degrees now versus 84. But again, we can rotate the phase triangle. We can't do that with that 3-element straight vertical array, the parasitic one. So what we get is we end up with 3 lobes of high gain, right? And each of those are at 96 degrees. So 96 times 3 is 288 degrees, okay? A full circle is 360. So we've got very few gaps where we're not, at better than 3 dB. So let's take a look at that real quick. So if you look at the right side of the screen, you see those 3 lobes. One's blue, one's green, one's yellow, okay? Those are the 3 lobes overlaid on the same pattern, okay? And you can see I've got it marked where you have 6 dB of gain going out the front of the lobe, and you can see where the beam widths are for the 3 dB on either side, okay? So the gap between those 2 little 3 dB gains is about 10 degrees in each of those areas, and that's all you're really losing, okay? Maybe 18 degrees. That you don't have 3 dB of gain. But over a single vertical, you're still 4 dB better at 10 degrees of takeoff angle, right? So this thing's going to be a monster compared to a single vertical, even in the dead areas. So, I mean, it's a great antenna, and you can build it for whatever band you want, right? Even if you build a 2-element, you can build it phase 2-element vertical and have it firing 180 degrees opposing. You can build it for whatever antenna, whatever band you want to operate. You want to operate 17 and have a loud station on 17, and you have 2 areas you want to try to reach on the globe? Build it, right? Doesn't take up much space, okay? Now, when you get to a 40-meter 3-element array, you're talking some real estate, okay? I'm going to be frank. It's a big antenna, right? You've got to space these things. The 2 elements in front and the 1 in the back, it's an equilateral triangle, and along those sides of the equilateral triangle, you're 1/4 of a wavelength. So for 7.2, the full wavelength is 41 meters, okay? So a quarter of that's 10.2 meters or so. So now you're looking at 10.2 meters, which is about 34 feet on each side. So you've got 34 feet, then you got the radial field underneath it. So even if you use 5-meter radials and you put a lot of radials down, you're still looking at 50 to 60 feet across and 50 feet on the top side. So a 50 by 50 square. Now you may not have room to do that, but I would venture to say most people have enough room to do a 20-meter one, right, with no problem at all. They can probably fit that because that's very small. I mean, you're talking about maybe 25 feet by 25 feet to put a 3-element triangular in for 20 meters. Now, if you're doing just a 2-element phased array for 40, yeah, maybe 40 feet and 20 feet wide. I mean, you can fit that in a lot of different places, right? And they're very inexpensive to build. And you're talking about some poles, and you can go out and get, fiberglass poles. You can't use anything that's conductive, but fiberglass, PVC, whatever, and you put it together and stand it up vertically. You just have a piece of wire running up and down it, and the way I built the 40-meter array is I used electrical box covers for my radial plate. I drilled 4 holes in it, got some stainless steel hardware, and that's where the 4 wing nuts are where I attach each of the radial pairs that go onto it. And then I bought a corner mount, 90-degree corner mount for the SO239. So it grounds down to the plate, and I just have a little spade connector that comes out, and I connect with a spade connector. I mean, it's probably $10 to $15 worth of hardware for each element, plus your radial, so let's say $30. So now you got $90 in that, and then if you want to phase it, you got $13 in a relay, a box, and a couple coax connectors. I mean, you're under a couple $100 for a darn good antenna. It's going to have you high gain. I mean, you're going to be challenged. Some of these guys have got beam antennas, and I can tell you, unless they got those beams up really high, that takeoff angle ain't going to be as low as yours, right? They're not going to have nearly the gain you're going to have at that low angle, okay? And like I said, it just takes the time and patience to build it. And then if you cut your own phasing cables, because phasing cables, if you buy them pre-manufactured, they charge you for the time it takes to cut that wire down. Even though it probably, once you did one or two, you probably do it in a few minutes. Yeah, they charge you an arm and a leg. I think DX Engineering charges about $100 for those things for one cable. So, but they have some labor involved, and it's a custom cable. And then there's basically what it looks like if you were to build it, right? And that's roundabout numbers. I found the numbers work better if I use 10.2 meters on each side and 9.02 meters on the vertical side of it. But those are pretty much it for the lengths of cable and how you put it together. Again, a 2-element is fantastic. If you can build it, if you got room for a 3, a triangular 3 like this, it's really easy to build, and it'll give you a good antenna. I mean, like I said, you can play with the big boys with that one. And we proved it on field day. That 40 meter on field day was an absolute monster. I just felt bad I didn't have a long enough control cable for the 20 meter, because I had a 20 meter built and ready to go as well. If we'd had both those 2 antennas up there, Lord help us, the contacts would have been crazy. So here's the diagram for switching the 40 meter parasitic, and you can do it a couple different ways. I just happen to have some 2-pole relays at the house, so they're double throw, double pull. So you have basically coming in, I feed from the radio into one side of the relay at the common point. I have the normally closed going straight out to the element antennas, okay? The normally open side, I have it going out to the phasing output. And then that phasing cable goes between the phasing output and the phasing input. Then it comes back in and goes into the normally open side on the other side of the relay. And I connected the common side of that second pole to the element outputs. So basically, if you understand how a relay works, when I turn the power on to that relay and it goes from normally closed to normally open, both those switch at the same time. So I only have one path for that signal to follow on that relay, right? I don't need any diodes. I don't need any funky kind of circuit in there to protect it from feeding over onto other elements. It's one path and one path only, okay? If you used single pole relays, you'd have to put 6 relays in there, or a bunch of big diodes, one way or the other. It's your choice. I would do it because of the RF power. I would do it with 6 relays, okay? And quite frankly, I mean, I had it set up with, this was a switching box I built, and this basically is just a 4-position rotating switch. I had LEDs telling me where it was at. I had a connector here, 4-pole connector. Each one carried a positive out to each of the relays and a common ground. And I had an on-off switch just so I knew it was on or off by the light being on it, so I knew the antenna was powered up. And then this is a very simple box, and I have my 3 elements. Radio comes in this side, control cable. Element 3's here, element 1 here, element 2 here, and then my phasing cable clips onto here. So this box would work for 20 meters, 17 meters, 40 meters, 80 meters, whatever one you wanted to build it for. The box is universal. It's just that phasing cable that's cut for it. It's that easy. The wiring is not hard to do if you can solder a little bit. It's not hard, and I'll let you take a look at the inside of that box. That's what it looks like. It's not complete. I don't have all the connectors on there, but that's what it looks like. Those are 3 double pole relays. And like I said, it's very simple to build. There's no mystery to this thing, right? Again, if you were going to do something where you were going to change the lengths of the antennas or you were going to feed multiples, that becomes a little more tricky. You start having to adding in LC networks and coils and things like that to fool the radiators into thinking they're longer, short, or whatever than the driven element, okay? But if you're just doing one element, then all you need is that 71-degree phasing angle, and we're using basically a power dividing circuit to feed 2 in phase and 1 reflected. So we have 2 in phase and 1 71 degrees behind it to give us the interference we want to steer that beam where we want it to go. And that's basically it. We have any questions?
So on your first example, just the reflected.
For the parasitic 2 element?
Can you go back to that? Maybe?
Yeah. Sure. And you know, all those things with the 2 elements, they're always a quarter wavelength apart. When you go to the 3 element, that's a little different piece of math. Because the reflector is going to be a quarter wave away, the director is going to be a little bit closer. It's like 15% of a quarter, or 85% of a quarter wave. Okay.
Okay, so you said the reflector is rounded or shorted?
Yep.
So your vertical, your essentially your driven element is shorted to your ground.
No, your reflected element is shorted.
But on the reflector.
Yes, it's shorted. So you build a PL259, and you just short the shield and the center conductor together and screw it in there. That way it gives you the ability to change it. If you wanted to change it and drag your cables around, you could do it that way. Yep. Now, there is mutual coupling, okay? So the formulas for the length of the radiators is pretty close, but depending on the type of wire you have and how exacting you are on your measurement, those wires may be a little bit longer, maybe a little bit shorter. So you're going to have to play around a little bit, make some adjustments when you're tuning your antenna, because you do get mutual coupling. When you get mutual coupling, things shorten down, okay? So you can also do this. It's not as efficient, but you could put 2 radiators of the same length. So let's just say we're going to do 40 meters, because that's the numbers I have in my head because I've done so many 40-meter antennas. And I want 7,200. So I might build those radiators on each of the verticals for a two element parasitic, maybe around 9.95 meters, right? And I'm going to lay my radial fields down, and I'm going to feed one of them, and one of them I'm going to short. Now my SWR is going to be a little bit off, and my gain isn't going to be as good. My pattern isn't going to be as tight, but it'll work. It'll work pretty darn well. Now if you want it to be really efficient and work really well, then you make that one you want as a reflector, you make it longer, right? You want it to be the right length, so it does mutually couple correctly, and it does send a signal where you want it in a nice, neat pattern, and it doesn't, you know, you get good front to back reflectivity. Because when you start to mess with those patterns, right, that thing lobe will elongate, or it'll get fat, and it'll look more like an egg than it does a cardioid. So that's what you give up. It's not as efficient antenna. You don't get as much RF push as you would if you build it properly. Okay?
So I'm thinking of some practical examples. Obviously, like our field day, that's become a standard antenna for us.
One of the most obvious uses of these antennas, for especially for parasitic, is AM broadcast stations, right? WBT here in Charlotte, they have 3 towers sitting over there, right? And they end fire north, south, or they'll broadside it, right? But most of the time they're north and south. So they'll switch that thing back and forth and fire south, fire north.
So
okay?
Maybe if you were on a de-expedition, you wanted to push back to the U.S.
Well, and that's a really good thing, right? If you have a specific area of the country, so let's say, or a specific area of the world, say you got a friend in New Zealand and you want to talk to them, right? You can put a 3-element parasitic array, find your bearing for New Zealand, whatever it is, 200, and from here it'd be about 260 degrees. So you'd put that bearing on 260 degrees, put that reflector, driven element, and director in that direction. And heck, I might even put up a fourth one. I might put up 2 directors. And you're going to narrow that beam down probably to about 45, 50 degrees. And you're probably going to see 8, 9 dB of gain in that direction and that direction only. Or if you're on vacation, say you're on the seashore, right? And you've got a piece of land where you can put up the antennas. Man, you want to aim it at Europe. You figure out your bearing 35 degrees, put that baby right there, and you'll hold a pile up into Europe all day long and all night long. That's the practicality of it. I've actually considered building one of these for St. John for 20 meters if I can find a spot close enough to do it, or big enough to do it. The property around the houses down there are pretty small, so it's a little hard to build that on level ground. The other nice thing about verticals, right? So if you do go de-expedition, right? Time you get around salt water and that conductivity of the soil goes up, the better those things radiate and the more that lobe comes down, right? So if you're able to get on a beach somewhere and put one of these things up, and that lobe will lower down to 2 or 3 degrees takeoff angle, and you will have monster gain. I mean, you're talking about what you're seeing at 20 degrees is now down at 10, 12 degrees. I mean, and you gain a lot more with the conductivity of soil because the soil becomes reflective at that point in time. So now those big lobes go out. So where you might be here getting 5 dB gain out of that antenna at 27 degrees, you might be getting 8 or 9 dB of gain at 10 degrees down on the coast, right?
And that is the equivalent of running 100 watts and say now you're at 400 watts.
So let's just take 9, yeah, say 9 dB a gain, okay? So I'm putting 100 watts in, let's minus the coax loss, because you're going to have a little bit of loss in your coax and the reflectivity, because you're not going to have a 1-to-1 or 1.0 to 1 or SWR. But let's just take that out and just say that's all perfect, okay? So I've got 100 watts hitting that antenna. At 10 degrees, at the max gain point of that antenna, if I have 9 dB of gain, that 100 becomes 200, that 200 becomes 400, that 400 becomes 800. So now it's equivalent to running an 800 watt amplifier off that point, right? And then your 3 dB bandwidth, you're still at 400 watts here. Even if you go back to 6 dB bandwidth or beam width, right? You still have 200 watts. That's how good those antennas are, right? But again, you start looking at when you put more and more elements, that beam width narrows and narrows and narrows, and that cardioid, the more it narrows down, the faster it drops off, right? So that's why that beam width gets pretty narrow quick. And you may get to a point where your beam width's so narrow, you only have a 3 dB drop, and then it's back down. You've got nothing usable at that point in time, right? One of the things I had on here was where that 3-element vertical was compared to the 3-element straight line parasitic compared to the 2-element phased, where that dB, where that 3-element went to unity gain, I still had 2 dB of gain on the phased array because the beam width was wider. I didn't have as much max, but I sure had a wider area to beam that thing through. So if you're trying to get, say field day, you build this thing, you point it up for the northwest or the northeast, you might not be as loud as you would be at one point with the 3-element, but you're going to have a wider area where you're going to be louder over that wider area. Does that make sense? Anybody else have any questions?
So trees, we had a big field for what we had at field day, wide open spaces. Do
Buildings will eat some RF up. It's just like anything else. Our building's going to eat RF up. Trees will eat it up to some point. It depends on what type of trees they are and how much foliage they have, because trees are full of water, and water tends to absorb RF pretty quickly, right? So, yeah. So, even though you're coming off the ground at a low takeoff angle, as long as you're not sitting there with a forest in front of you or you're right up against your house, you're still going to get good propagation. It may not be as great as it was if you had, 50 yards around the thing, right? But everything's a compromise, right? Yeah.
Are you guys pretty close to those power lines too? Field day?
Yeah. We were a couple hundred yards off of them. It wasn't that bad.
They might not be being used.
Yeah. I mean, you're going to,
Those are transmission lines. You come out of the dam and you go this, or the nuclear plant go this way with it or that way. They're not always in use. So
yeah. Yeah, they're not always, when you have transmission lines, they're not always energized. But again, vertical antennas tend to be a little more noisy and they'll pick up a little more RF from that. But if they're built right and you have an isolator on there, chances are you're not going to hear any more noise than you would off a dipole. Now, if a loop, that's a different story. Loop's just much more quiet. Now, you're going to pick up ignition noise more on a vertical than you would. So if you have a lot of traffic around or you're running generators, you'll tend to pick up a little more noise. It just depends on proximity at that point. Anybody else?
does an antenna tuner help any of this?
You can, for these antennas, you're building them for a specific band and they're pretty broad banded, so you're going to be really resonant. At one point, you're going to be almost perfectly resonant, right? You're going to be at 1.1 to 1 or 1.0 to 1 if you build it right. For the most part, you're going to be under 2. So is it worth putting an antenna tuner in there? How much more effective am I going to be? Probably not much. So, yeah, you could put a tuner in there and use a tuner, but why? You're just adding more of a loss into it than you are anything else, and you're going to gain out of it using a tuner. That's why resonant antennas are so good, right? Because you don't have the loss on the two, so you don't have reflected power coming back at you. Very little loss in your signal. That's why the old timers, they run those old feed line 450 ohm or 600 ohm feed line up to these big long non-resonant dipoles, because they're tuning it there at the radio, and that stuff's lossless as it's going up. So, we're spoiled with coax. It's easy to run and it's easy to maintain and it's forgiving. And even when you run lossy coax, right, it makes the antenna look better than it really is. Yeah.
So your guys at WRTC, they'll run one dipole for one band.
Yeah.
They don't run multi-band dipole.
Yeah. A single resonant dipole. Yeah. What's that, Walt?
Your vertical fiberglass supports.
Uh-huh.
40 meters. You have to use about 43-foot vertical.
You can use a 10-meter pole and fold over the wire on the antenna and fold it over the top of the antenna. You have to allot for that, so there's some formula you have to figure in. If you use a 30 or a 10-meter pole and you've got a little bit more wire, you might have 18 inches or so wire that you have to deal with that's going to come back down. It's actually going to mutually couple, so that's going to be a little shorter than 18. Probably end up being about 12 or 10. But yeah, you can easily do that. And the way to fix that is if they have a little loop at the top, you can run that wire through there and just go down and tape it. Or you can get some aquarium tubing. If you buy a DX Commander kit, right, he has a 10-meter pole and he runs a 40-meter element up it. And it's just a loop, the pole's not actually 10 meters, it's like 9.7 meters. So it ends up being a little bit longer for the 40-meter. You fold it over and put a little piece of aquarium tube on it, holds the wire in place so it's not wiggling around. Or you can tie a little piece of fishing line on it and make it a short L, inverted L. And I've done that before, and that actually works great. Because what I found out with my DX Commander, and we're talking about two different things here. We're talking about multi-band antenna versus a single monoband. If I ran it and coupled it down, I was having trouble getting a tune on 15. But if I ran it as an inverted L, I got a really good tune on 15 and a good tune on 40. But that's particular to that antenna. But no, if you had a 10-meter pole and your line's a little bit longer, just fold it over and tape it down, and Yeah, you're going to probably have to adjust a little bit for it. So when you tune your antenna, and the best thing to do is tune them all for the band you want individually, then put them where they're going to be and tune it then. And you're going to make a few small adjustments, but you'll get it pretty close that way. If you try to tune it all at one time, it's a little more difficult because then you got to go and remember, I got 2 inches off this one, I got to cut 2 inches off this one, I got to cut 2 inches off this one, and those measurements don't get precise, right? If you're tuning one and cutting one, the measurements become precise. Anybody else? Okay. I think we're all done. David, do we have any questions back there? Nobody. Okay. Well, I guess everybody found it. I hope I kept everybody awake somewhat. Anyways, that's all I got for you folks tonight. So thank you very much. I'm looking for presentations for August and September right now. I have been trying to get Bob Howell to commit to one of those 2 dates, and I haven't been able to get him to commit. We do have the DX commander himself, Callum McCormick, will be here in October. So he's going to do a virtual presentation from Shetfield across the pond. So we'll have him in October. But it is 4 hours ahead, so it is a little after midnight.
You don't want to miss the DX.
Yeah, no. We're still figuring out what he's going to talk about, but we'll, and he was gracious enough. He sent us a 12-meter mast, fiberglass mast for our Hamfest. So, yeah, go give him some love on YouTube, and if you feel froggy, buy one of his antennas. That's enough for the commercial for that. David, I think that's it, so we'll close it out. Good night, everybody. Thank you for coming by, 7-3.